Okay, let's continue with the solution to the problem that was posed before. And I noticed that the statement of the problem is slightly different here than the one that I showed earlier. The one I showed earlier is the one you should have on your worksheet problem. So I'm going to pretend that this one says that. Two objects attract each other gravitationally with a force of 2.5 times 10 to the minus 10 newtons. Let's assume they're spheres and their centers are 0.25 meters apart. This version says their total mass is 4 kilograms, but the version that you should have says one of their masses is 4 kilograms. Find the other mass of the other sphere. Okay, and so we're just going to plug into this formula, F equals gm1 m2 over r squared. The F we know, G we know, one of the m's we know, the other one we'll just put in as a variable m. And the distance r is 0.25, so we got to make sure we square it and all that and solve for m. And we get m is 0.0586 kilograms, or in terms of just grams, even though that's not an SI unit, 58.6 grams, so a fairly small mass. All right, so those were some simple examples of calculations, but if you start thinking about it a little bit, you might get confused about how you know what to do here. I can calculate the force between objects if I know their masses and separations, but if we're talking about the attraction between Earth and Moon, how, for example, do we know the value of Earth's mass? I mean, you can't exactly put Earth on a scale and weigh it, or you can't take Earth and shake it and see how much inertia it has. We can't do those kinds of experiments, so how on earth would someone know how to do this? Well, the answer is if you watch something go around it, you can back out what the mass of the object that is being orbited is. So what goes around the Earth? Moon does. So I guess, I don't know if this is supposed to be m for moon or m is the mass of the object. I think it's just the mass of the object. So here's an object of mass m. It's really moon going around Earth. If I I'm sort of being lazy here. I just turned my diagram into a mini free body diagram for mass m. It's got a gravitational force towards Earth. I'm going to take plus x toward the center of the circle, as I always do when we're talking about uniform circular motion, because I know what the acceleration component is along that direction. And then do sum of the force x components equals max. There's only one force acting on mass m. It's the gravitational force from Earth, and we know how to calculate it now. G times the mass of Earth times the mass of Moon divided by the distance from Earth to Moon. I wrote that as REM, distance from Earth to Moon, squared. Okay, that's the only force acting on it, and in my coordinate system, it's a positive x component. That's equal to the mass of the thing in the free body diagram, that's the mass of the moon, times the acceleration x component, and the acceleration is towards the center of the sphere, so the entire magnitude of the acceleration, which is v squared over r, is just a positive x component. And so here, the speed, the Vm is supposed to be the speed of the moon squared, divided by the distance from the Earth to the moon, because the distance from the Earth to the moon, or at least between their centers, is the radius of this circle. Okay, so first thing we can do is some cancellation. I know that the mass of the moon appears on both sides, so it cancels out. The second thing we can do is, I don't know the speed of the moon around Earth directly, but we can calculate it again by the distance over time trick. I know how long it takes moon to go around Earth. That's 27 days. So the time I'm going to use in calculating that speed as distance over time, the time I'm going to use is 27 days. In each day there's 24 hours. In each hour there's 60 minutes. In each minute there's 60 seconds. So that's how many seconds there are in 27 days, which is the time it takes the moon to go around one orbit. And how far does it go during that time? Exactly one circumference. 2 pi times the distance from Earth to moon and so that's one circumference. That V needs to be squared, so that whole mess needs to be squared. And now we can solve this relationship for the mass of Earth. Now you might say, well, how do we know the distance from Earth to Moon? Well, at least in, it was at one time a complicated procedure, but not right now. The way we do it is, when astronauts landed on the Moon, they put something called a corner reflector on the Moon, and a corner reflector has a neat property that when you shine something at it, like a laser beam, it shines back that beam exactly in the direction it came from. So, with this corner reflector placed on the surface of the Moon, we can shine a laser beam at the Moon, and that laser beam spot will come right back to the laboratory that sent it out. And by measuring the time it takes to go there and back, we can figure out what the distance is if you know the speed of light, and that's another measurement someone can make. So there are pretty easy ways nowadays to measure the distance from Earth to Moon, kind of like that. So I'm going to solve this big mess for ME and calculate ME, and we get ME is 6.2 times 10 to the 24th kilograms, very close to the value that's in the back of your book for the astronomical data. All right, there's another problem. This, it's easy to make things look simple when you first start out, and then the more you think about them, the more confusing they get. Sure, I can determine the mass of a planet by watching something orbit it. We just saw how to do that. Excuse me. The question now is, well, how do we know what capital G is? Because look, the way we're doing this, ME was an unknown that we were trying to solve for, but how does anyone know what capital G is? Newton couldn't just pull it out of the hat. And so we can't really solve for the mass of the Earth in that procedure we just did unless we know what capital G is. And the answer is, at first, Newton didn't know what capital G was. He just knew it was a constant, but he didn't know what the constant was, and so he couldn't solve for the mass of Earth. So Newton didn't know what the mass of Earth was. He just knew that this was one big unknown, this product right here. And how do we determine what capital G is? Well, in order to do that, we can't use things with unknown masses. We actually have to measure the gravitational force of attraction between two known masses that we can measure in the laboratory. And so the clever experiment that actually did this to a convincing degree, because the gravitational attraction between two masses that we can pick up in the lab is very, very small. That's a consequence of the fact that capital G is so small. So it's really difficult to measure forces that small, but here's the method by which it was done. We have to measure the gravitational force between two small masses. How do we do that? The first experimental apparatus, and it still is something that people use to measure capital G, is called a Cavendish balance, and it's able to measure very small forces. Here's what you do. You have two huge spheres of lead, and huge, they could be like sort of softball size, but lead is very dense, so those would be really massive spheres of lead. And you place them at certain fixed locations. You're not going to touch them. And then you have some smaller spheres of lead that you attach by, a not too heavy bar. And at the center of the bar, you have a light string going up, which you attach somewhere up above. And the idea is, at first you remove these heavy masses, and you control for all the air currents in the room because they might push those masses around. You make sure that nothing is moving the air at all. You let the thing go and you just let it settle down until it's totally happy and stationary. And then what you do is come and bring in these two masses. And what happens? Well, this mass is attracted to this mass. This mass is attracted to this mass, and they cause this thing to twist. Now, normally you wouldn't be able to measure that twist, but a little thin piece of string doesn't have much resistance to twisting a little bit. And by by knowing how much force it takes to twist this very, very subtle string, and measuring how far this mass moves towards that one, and it's not a quick process. You set these masses there, and you'll find out that this thing oscillates extremely slowly. So it gets closer to it, and then it gets farther away, and then it gets closer, and you have to wait hours for it to settle down. But eventually it will settle down so that this one is closer to this one, and this one is closer to this one. And by measuring that distance that it's moved and knowing some properties of the string, you can actually measure that very, very tiny force. That's called a Cavendish balance. And Cavendish was so thrilled that he could do this, he made the claim, "I have weighed the Earth for the first time," because he knew if only I could figure out what capital G is, then I could figure out what the mass of the Earth is from our previous calculation. That was known at the time. So he says, "I have weighed the Earth." That was a huge deal at the time. So another amazing thing, just like Eratosthenes measuring the radius of Earth, here's a measurement of capital G, which allows us to calculate mass of Earth. Another interesting thing that, was sort of coincidental in our earlier work, we said little g is the acceleration of an object at the surface of Earth towards the center of Earth. And that was just sort of a random number that we could measure experimentally. We could measure that acceleration with which it drops in free fall, but there was no explanation for why little g is the value that it is. Now in Newton's theory of gravitation, little g can actually be calculated. So little g, the value 9.8 meters per second squared, is a consequence of Newton's theory. So that explains things at a deeper level. There's still new mysteries. You might ask, well, then why is capital G the value it is? But at least it's explaining it at a deeper level. So what we're going to do to determine this value for little g is calculate the force. If we imagine letting an object of mass, we'll call the mass of it m object. We're going to let it go and free fall towards the Earth. And let's calculate the force on it. One way we could calculate the force is the old way. We know the force on it was just the mass of the object times little g. But let's also calculate it the new way, which is gm1m2 over r squared. So capital G we know the value of. The Earth is one of the masses that's doing the attracting. The other one is the mass of the object. And if that object is at the surface of the Earth, the distance from that object to the center of Earth is the radius of Earth. So we have to divide by the radius of Earth squared. We can cancel out then the mass of the object and solve that. Then when we cancel that, we're left with the value for little g. Oh, I'm not sure what's going on there, but it disappeared. So we can calculate little g is g times the mass of the Earth divided by the radius of the Earth squared, and that's about 9.8 meters per second squared. The value of little g actually varies from point to point on Earth. Some places on Earth it's closer to 9.81. In Danville, Kentucky, it's very close to 9.80 meters per second squared. So, if you meet someone from Paris, they might say 9.81 meters per second squared. But in any case, it's very close to 9.8 meters per second squared on the surface of Earth. Now we could take this same calculation and say, well, I would like to know what little g is on the surface of the moon, right? With what acceleration do things accelerate towards moon if we drop them at the surface of the moon? And we could just say, oh, the only replacement I need to do is, this would be now g on the moon. We would have the mass of the moon here, and this would be the radius of the moon. And so if you know those values, you can calculate what g is on the surface of the moon, and it's about 1.6 meters per second squared, about 1/6 of the value of what it is on the surface of Earth. So we can calculate it on Earth, we can calculate it on the surface of the moon. You can calculate it anywhere as long as you know how far you are away from the important gravitationally pulling body in the region. And so in Newton's theory, we're going to think of little g as something that varies from point to point throughout space. Okay? If you drop something at that point in space, the meaning of little g, which is a vector, is the magnitude of it is how fast it accelerates, and the direction is the direction in which that object would start accelerating when it's released only under the influence of gravity. So, for example, if you talk about Earth's gravitational field, that's what we call this value, little g, if we picture it as something that is around an object. So here I'm imagining, here's Earth. things accelerate a lot when they're close to the Earth. If you get farther away, they don't accelerate as much, but they always accelerate towards the center of Earth. So this would be sort of a picture of what the gravitational field looks like around Earth's, immediate neighborhood. Okay, let's try two more problems now on the worksheet that we've been working on. Problem 2, given the acceleration of gravity at the surface of Mars is 0.38 of what it is at Earth. Okay, so I know what, at Earth it's 9.8. On Mars it's 0.38 times 9.8. And Mars's radius is 3,400 kilometers. Warning, that's not in SI units. That's, SI units are meters, so you have to take that into account. Can you use that to determine the mass of Mars? And 3, a hypothetical planet has a mass of 2.8 times that of Earth. Okay, we can look up what Earth's mass is so we know what the mass of this planet is. It also has the same radius. So what is little g near this planet's surface? Well, you can calculate it using that formula. The radius is going to be the same because this planet has the same radius as Earth, but the mass is going to be different. So we can calculate what little g is near the surface. So try those, and we'll be back with the solution.